Welcome to our discussion on growth, looking at the differences between linear and exponential. So linear growth occurs when some quantity grows at a constant rate, right? So it grows by the same amount over each unit of time. So the same amount per day, per week, per year, per month, whatever. Exponential growth occurs when some quantity, right, whether it be money or, you know, um, cells in a petri dish or whatever, grows by the same relative amount, meaning a percentage. So it grows by the same percentage each unit of time. And what happens is linear growth has a nice straight line, and exponential growth has this funny curve. And you can see that because of that, it grows a lot faster. In fact, right, if they both started at 10,000, if you take this 20,000 line out here, the straight right increase doesn't double until 20 years later, whereas this one doubles at like 14 years later. And then doubling again to 40,000, right, happens at like 27. But if you take 40,000 out, it hasn't even happened, right? It's not going to happen until probably closer to 60. So it grows a lot faster when it's exponential. So in each of the following situations, let's see if we can state whether the growth or decay, right, is linear or exponential, and then answer the associated questions. So the first example is the number of students at Wilson High School has increased by 50 in each of the past 4 years. If the student population was 750 4 years ago, what is it today? So it's increasing by 50 students. The price of milk, however, has been rising by 3% per year. And if the price of a gallon of milk was $4 a year ago, what is the price now? So which of those two is increasing by a constant amount, and which one is increasing by a constant proportion? Remember, proportion is a simple word for percentage, right? So obviously going up by 50 students is a constant amount. Going up by 3% is proportional. How about C? Tax law allows you to deduct the value of your equipment by $200 per year. So you can take $200 off every year. If you purchased the equipment 3 years ago for $1,000, what is its depreciated value today? How about the memory capacity of state-of-the-art computer storage devices is doubling approximately every 2 years. So if a company's top-of-the-line drive holds 16 terabytes a day, what will it hold in 6 years? And finally, our last solution, the price of high-definition TV sets has been falling at about 25% per year. If the price is 1,000 today, what can you expect to be in 2 years? So out of these three, which one, if any, is increasing or decreasing by a set amount, and which ones are going by percentages, right? And remember, doubling is the same thing as a 100% increase. So there's a hint. Okay, so here are our solutions. Number of students went up 50 each year, so that's linear. So in 4 years, it's just going to go up 54 times. So 50 times 4 is 200. You add 200 to 950, and there you go. The price of the price rises by 3%. So this is exponential growth. If the price was $4 a year ago, it increases by 3%, 12 cents, making the price $4.12 in 1 year, right? If we wanted to figure out what it would do in 2 years, then we would have to take $4.12 and multiply that by 3% and add that much back, right? Or basically multiply it by 103% each year. C, you can decrease, right? The decreased amount is $200 each year, so that's linear. So we just do 200 times 3, and we get to write off $600. So the value goes from 1,000 to 400. Doubling is the same as 100% increase. Remember, I told you that as a hint. So if it doubles, right, 3 times in 6 years, from 16 to 32 terabytes after 2 years, from 32 to 64 after 4 years, and from 64 to 128 after 6 years. So there's your 3 doublings. And then E, it decreases by the same percent, right? Goes down by 25%. So it goes from 1,000, take away 25%, now it's 750. The following year, the price will fall again by 25%. So you take 25% of 750, which is 187.50. You subtract that, and it'll now be down to $560.50, or almost half price, right, in 2 years. So suppose you place a single bacterium in a bottle at 11 a.m. It grows and at 11:01 divides into 2 bacteria. These 2 bacteria each grow, and then 11:02 divide into 4 bacteria. At 11:03 they divide into 8 bacteria. So you can basically see it's doubling every minute. So now suppose the bacteria continue to double every minute and the bottle is full at 12. The number of bacteria in this point would be 2 to the 60th because it doubled every minute. So, it went at 2 times 2 times 2, basically 60 times. But the important fact is that we have a bacterial disaster on our hands because the bacteria have filled the bottle. The entire bacterial colony is doomed. But really, it's if you do 2 to the 60th, that's a huge, huge number. Okay. So the disaster occurred because the bottle was completely full at 12. When was the bottle half full? Well, remember, it doubles each minute. So it was half full at just 11:59. So you were just, 1 minute away from a disaster if you had stopped the growth at 11:59. How many bottles would the bacteria fill at the end of the second hour? Well, they've doubled, right? They filled 1 bottle at the end of the first hour. So each minute they're going to double. So as they continue to double, they fill that many bottles, right? So in 1 minute, they now fill 2 bottles. And then it doubles again, and so on and so on and so forth. So in another 60 minutes, you have another 2 to the 60th, which is 1.15 times 10 to the 18. That's got 18 zeros after that first one. So basically 16 zeros after the 5. That's a huge number of bottles, right? So at the end of the second hour, the bacterial will fill approximately 10 to the 18th bottles. If we work with powers, we can write 10 to the 18th equals 10 to the 6th times 10 to the 12th. We know that 10 to the 6th is 1 million, and 10 to the 12th is 1 trillion. So it's a million trillion bottles, or more than anybody could ever count or even create. So you can see that exponential stuff can grow very, very fast. That's the whole point of this silly little example. So the key facts, right? Exponential growth leads to repeated doublings. Things double, and so we call that doubling time. We calculate how long something takes till it doubles, and we call that its doubling time. And exponential growth cannot continue indefinitely because the numbers just get too big. Right? I mean, technically they can, but in the real world, things tend to not double forever, right? Okay, and that's everything you need to know about linear versus exponential growth.